Let's now walk through a full example of limited tiered execution. So we're going to look at how system calls work, how your context switch works, and then like how the whole thing works together with the hardware, right? So there are going to be multiple moving pieces here. So let's just start off with like what happens when your processor is sort of like booting up and your operating system is setting everything up, right? So first we're going to talk about the boot up process. So when the processor is booting up, it's going to be in privileged mode, right? So I'm going to use just this to indicate whether it's in kernel mode or not. So initially, here 1 means that it is in kernel mode. So initially, the booting up process, the operating system is running, it's in kernel mode, right? There's no application code that's actually running at this point of time. So some of the things the processor will do is that in your processor, the operating system will do is in your processor, there will be these like interrupt handling tables, those will be getting set up. There will be your trap tables, those will be getting set up. So these are to ensure that when there is a later system call or a trap or a timer interrupt, it knows how to handle all of these things correctly, right? So because it's in kernel mode, it knows that only the operating system can actually set all of these things up correctly. So at the end of this process, it's set all of these things up, and at the end of this, it basically will move to kernel mode. To user mode. So in kernel mode, it has set everything up. So that's really the start of this whole thing, the boot up process. Now let's actually look at something else. So now let's look at what all the different things that are going to happen as we move to through different things. So we're going to have this particular scenario. We will have our familiar P1, and then we're going to have the OS, and then we're going to have P2 run. Okay, so this is the same sequence that we have looked at before, but with a slight difference. So the way P1 is going to be interrupted is via timer, and the way P2 is going to be interrupted is because it's going to do a system call, and these will involve slightly different processes, right? So let's look at like what everything looks like at this point of time. So you have P1 running, and then kernel mode is 0, right? Because like we're not in kernel mode. So P1 has its set of registers. It has its stack, and then it has its heap, and then there's all the other stuff that's in that's in kernel mode, right? So this is all the kernel part of it, right? Heap, variables, and so on, right? So the timer interrupt fires, and when the timer interrupt fires, you have your processor, and then inside you have the interrupt table that the operating system set up in sort of like our previous slide. And then what this basically says is, oh, we have a timer interrupt, run the OS. Okay, now before you can actually go ahead and you can run the OS, you need to do context switch, right? Without saving the state that's in this particular process, like there's nothing else that can be done. So the first thing that really happens is that the state of P1 is saved in the kernel stack at this point of time, right? So whatever the registers that P1 was using, like wherever the instruction pointer was, wherever the stack pointer was, everything is captured and is saved as a context in the kernel stack, right? So let's just call this like P1's context. So now this has been saved. So the benefit of this is that like we can now resume P1 at any point of time. There's not going to be any loss of information. So that's done. Now we can actually go ahead and we can run the OS itself. Now the OS when it's running is going to use this stack, right? So it's going to have different functions, it's going to run different things, it's going to use this stack. And let's say it uses the stack to run a function foo, and then it decides that it wants to run P2, right? So it's still in this part of the code, right? Now, to run P2, you basically need to find on the stack where P2's context is, right? So let's say it finds the context of P2, and then P2 is basically then restored. All the registers of P2 are restored, and then at this point of time, there's a context switch that happens, and from the OS you start to run P2. Now, at some later point of time, your P2 runs and its registers have changed, right? So let's say that it was like looking like that, and now it's changed a little bit, right? So P2 has changed its registers. I guess a system call. Now, at this point of time, once again, if you look at P2, it has there is a kernel stack, right? And this new state is once again saved as context in the stack. At this point of time, P2 has been successfully saved, and it can be restored at a different point of time. Now, if you look at the overall state of the system, there is P1's context, which is just sitting around, there is P2's context, which is just sitting around, and then the OS, of course, has its own stack. So at this point of time, we can successfully run P1 or P2 or the OS with no problem at all, because we have enough context to run any one of these processes, right? And so of course, to the user, right, all this could happen very quickly. So this could be like 0.00, and this whole thing could have happened by 0.01. So within like 1 second, the P1 timer could have fired, and then the OS could run, and then the P2 could run and could have done a system call. So to the user, it will look as if like P1 and P2 are making progress, even though what we're doing is really quickly time slicing P1, OS, P2, OS, P3, and so on, right? So that's really the sort of like high level overview of like how the limited direct execution works. So we looked at both the context switch part of it and the system call part of it, and all the different hardware bits that need to cooperate to allow limited direct execution to happen. So next we're going to be looking at the scheduling policies that the operating system has.